features. So before we move on to Arun's presentation, allow me to just give a give a very quick introduction. Arun is a cybersecurity software developer working here at the Canadian Institute for Cybersecurity. He holds a master's in computer science for the University of Louisiana and a BTech in biotechnology from Indian Institute of Technology, Guwahati. With over 5 years of professional experience, he's specializing in designing analytics frameworks and developing software solutions. His current research focuses on anomaly detection to combat stealthy attacks in heterogeneous IoT environments and on post-quantum cryptography for securing resource-constrained device against future quantum threats. Arun, welcome to this part of the session.
Thanks for the introduction, Sumit. So as Sumit mentioned, my presentation is on Beyond Packets, Unmasking IoT Attacks Through Flow-Based Features. So my colleague, Dr. Mahdi, had already presented, discussed his an approach our team used for packet-based feature extraction process. So this is an additional approach our team explored to using flow-based features. So the outline of the presentation is going to be as follows. So first I'll share the motivation on why flow-based metrics are a good approach for such problem. Next, I will move on to the corpus that we used as the network capture files in PCAP format for the feature extraction process. Then our flow feature extraction pipeline on how we turn these PCAPs into per flow statistics. Following this, we move on to the flow-based feature set. Then we move on to the experiments we performed with the dataset and the results we got. And finally, we wrap up with the research applications that we believe it can be used for and the conclusion. So for the motivation, as we all know, in today's growing IoT environment, threats are increasingly becoming stealthy and diverse. So many adversaries exploit the fact that payloads are often encrypted and or proprietary. And then secondly, IoT deployments are currently in heterogeneous environment. So like a one-size-fits-all packet deep inspection won't scale. Then devices also face severe resource constraints. So, making large models infeasible on most live environments. And finally, there is a gap in existing datasets as few publicly available datasets capture both the benign and attack scenarios at flow granularity. So these challenges motivated us going for this particular approach. So now, moving on to the corpus that we use. So we made use of the CIC IoT 2023 dataset. This was constructed from real-world IoT devices deployed in a large-scale testbed. So the subset of these devices were compromised to execute different attacks, and these were captured in PCAP format. And then these attack categories were grouped into attacks were grouped into 7 categories based on the tactics like flooding, which contains DDoS attacks and DOS, and then probing attacks like reconnaissance, then web-based attacks, brute force, spoofing, Mirai malware, etc. And also in the same time, benign traffic was collected in addition to the attacks collected. The dataset included extensive periods of normal traffic. So being able to capture the benign data gives the necessary contrast for anomaly detection. Now, moving on to the flow extraction process. So flow-based analysis essentially collects the essentially process the metadata that is available rather than the actual payloads, thereby delivering scalable and privacy preserving visibility into network behavior. So here you trade the like the forensic depth of full payload inspection for speed and scalability here. So one record per flow rather than multiple packets. So that means you can run anomaly detection in real time across environments with a huge number of devices. So in short, what you're getting through flow-based analysis is anomaly detection of attacks at a scale, fast and efficiently with minimal privacy impact. So now let us try to define what is a flow. So a flow is essentially a group of packets transmitted between two endpoints, client and server, over a protocol. So it is essentially like a 5-tuple that includes source IP, destination IP, source port, destination port, and protocol. So you can think of it as one conversation. For example, your phone talking to a web server over HTTPS. So here you can see a Wireshark screenshot of a HTTPS interaction. So in the first step, you can see the TCP handshake happening, where you have the SYN ACK, and ACK. So these from these packets, we are able to harvest header level features like time to live, initial window size, sequence numbers, etc. Then moving on to the key exchange. So once the TCP handshake is established, then it moves on to the TLS part. So the client would issue a client hello, and the server returns a server hello. And in this, we can record the length of these packets, the list of the cipher suits, the length of extensions, and the list of extensions and signatures. Then moving on to the encrypted application data. So after these handshake, application data flows encrypted through these TLS records. So while we can't see the content, we can still capture rich statistics like the number of encrypted packets, inter-arrival times, packets per second, etc. Then when we move on to the four-way handshake, so this happens when essentially the session ends. So the four-way handshake, FIN ACK handshake closes the flow. So we can log many, like how many flags have occurred and the timing between them, etc. So in essence, we can aggregate a lot of features, which include all the type of service values, all the flags, window information, options, etc. So this is being done here using CIC Flow Meter, which is an open source tool created by CIC. So this systematically converts these raw packet capture files into bidirectional flow records. So this bidirectional flow analysis allows it to calculate statistical time-related features separately for both forward and backward direction, which provides a comprehensive understanding of the flow. So it accepts as input a directory of PCAP files, and through configurable parameters, it converts all these packets into flows that, like all the packets that share the 5-tuple, will be converted into discrete flow objects. Then, like here, you can see an HTTP session in Wireshark. So the upper panel here displays a typical Wireshark trace, which contain all the handshakes, the TLS exchanges, encrypted application data records, and the TCP four-way teardown. Now, each line here corresponds to a single packet event with the full header and payload details. Now, then here we are highlighting all the packet events that will belong to one flow. So CIC Flow Meter, it will collapse these dozens of lines into a single flow record, thereby reducing the data dimensionality. Then following this aggregation, each flow will be represented as a fixed feature length vector. So here you can see a flow ID column and subsequent columns from F1 to F76, which will contain quantitative metrics about the flow. Then finally, CIC Flow Meter will explode these flow records into CSV files, which can be inspected in a spreadsheet or ingested into data science toolkits. So here you can see real flow entities with fields for forward and backward packets, then byte totals, flow duration, and other statistics. So now let us try to place the flow extraction within our comprehensive pre-processing flow. So First, PCAP files were processed by CIC flow meter to generate these flow records. Then our feature extraction scripts compute a total of more than 80 statistical features per flow. So these descriptors then undergo pre-processing and data cleansing and etc. to produce a streamlined feature set. So these resulting CSV tables constitute the input to machine learning models that can be used for the anomaly attack detection problem. So now let us just move on to the actual dataset features. So like so every flow record will have over 80 statistical features. These would include basic flow identifiers like the phi tuple. Then another important set of features are the inter-arrival time features. So these are based on time intervals between sequential packets within a network flow. So these are the set of inter-arrival time features. So there are three types of inter-arrival time features here. One is the inter-arrival times between two packets sent in the flow. Then you have inter-arrival time features for two packets sent in the forward direction and two packets sent in the backward direction. So these features are important because this helps you understand various time delays that might be happening between packets in a network session, which can be indicative of certain abnormalities. Then moving on to the next set of features. So these include flag features. So they basically calculate measure the existence and frequency of specific TCP flags in the packets. So there are two kinds. So sort of calculate the number of PSH flags sent in the forward and backward direction, then the urgent flag that are being sent in the forward and backward direction, and then certain other flag counts here. So by monitoring the frequency of such flags, it is possible to distinguish between normal and abnormal terminations or some kind of SYN flood attacks, etc. Then moving on to the next set of features, those are active idle features. So here we collect features from both active and idle TCP flows. So these are the main features that are involved here. So in this, active means something which can be helped in identifying abnormally idle or active duration, where then even active max can be used to identify good insights about the upper limit of flow activities, and as a result maybe detect anomalies based on longer connections. Then moving on to segment, bulk, and byte. So these features sort of provide insights about the size of the data flows. So these can be grouped into four, which are segment size averages for forward and backward direction, then bytes per bulk average in forward and backward direction, then packet per bulk in forward and backward direction, and finally for bulk rate average in forward and backward direction. And moving on to the final set of features, those are other statistical features which sort of give you information about the flow. And so to be final, these are the set of 84 features that we generated using this process. And and now let us move on to the experiments we performed with this feature dataset. So the dataset had about 2.3 million flows, which included both benign traffic and 7 kinds of attacks. So we framed 2 detection tasks here, both a binary anomaly detection of attacks. So the first kind was a benign, trying to classify a benign flow against any kind of attack. And the second kind was where only one kind of attack was used against benign to be detected. So we, to benchmark, we trained 5 off-the-shelf classifiers like XCG-boost, decision tree, random forest, multi-layer perceptron, and logistic regression. Then we also tried to apply RFE, recursive feature elimination, to retain the top 40 most informative features to see how it performs in a more streamlined approach. And also, additionally, to evaluate, we utilize standard metrics like accuracy, precision, recall, and F1 score. This is the results that we got against in the first set of experiments against all attacks. So you can see here that XCG Boost is the best performing classifier with about 95.92% accuracy using all the features available, and 95.85% with just the 40 features, while cutting the test time from around 6 seconds to under 3 seconds. Random forest is also nearly identical, but the training time is a lot larger. So the key takeaway here is that our flow-based feature representation enables a high accuracy across millions of encrypted flows, and also that recursive feature elimination, the feature selection process we used halves the feature set with negligible loss, making real-time edge deployment practical. Then using XCG Boost, we also perform the per attack classification. So here, for each threat, we trained on both the full set of features and also the 40 features selected by RFE. So notice that across every attack, pruning to 40 features barely changes accuracy or F1. Like brute force stays at 99.6% accuracy, and DOS and Mirai remain about 99.8%. While at the same time, while using RFE, the test times are shrinking by roughly half. So this demonstrates that a carefully chosen subset of flow-based metrics will deliver the same detection power as the full set while cutting the computational cost, which can again be crucial for real-time or edge-level deployment. Now, moving on to the conclusion. So, we essentially leverage the existing flow data, like the data set available with CIC IoT. And by focusing on flow-based features, we were able to condense the IoT traffic into a compact set of actionable data. And then also trimming to the top 40 features by using RFE, we are able to maintain peak detection accuracy while slashing the computation costs. So this sort of validates that flow aggregation is a powerful privacy-preserving approach for IoT anomaly attack detection. Now on to the future direction. So as we look ahead, there are several promising avenues to extend this flow-based approach. First, we can explore more sophisticated modeling techniques that capture relationship across devices and flows, which can help in uncovering patterns that flat feature vectors may miss. Second, adding explainability layers would triggered and helps in speeding incident response. Third, we also aim to push our detection models down to edge so that we can score flows in real time on IoT with minimal overhead. And finally, constructing temporal flow graphs and applying graph embedding techniques may reveal more slow burn threats that evade these snapshot based detectors. So together, these directions will make flow-based IoT security more accurate and practical for real world deployment. So thank you for taking the time to hear the talk. And maybe Sumit, if there are any questions, I would be able to answer it now.
Thanks for that, Arun. That was a nice continuation to what Madhi started with the discussion on this particular data set. So thanks for your presentation. Let me just see if we have any question. We certainly do have some. So just a minute. The first question is, why emphasize the anomaly detection flow-based feature sublet for anomaly detection rather than the pocket level feature?
Thanks for the question. So yeah, it essentially comes down to efficiency and practicality. So sometimes, it might be difficult to inspect per packet payload across a lot of devices. So flow-based aggregation here would allow you to collapse a lot of packets into one metadata record per conversation. So this would essentially cut the data volume by orders of magnitude, which makes it feasible, it's feasible to run on resource constrained or edge devices in real time. Plus, also flow features are mostly rely only on headers, timings, and flags, etc. So there is no need for decryption. And packet level features, in contrast, may sometimes require deep inspection, which doesn't always work on streams, or sometimes might not scale on an IoT network.
Thanks, Arun, for this for this explanation. We do have a lot of questions, but we just don't have the time to take all those. So unfortunately, with this, we'll move on to the next speaker. And before we do, thanks, Arun, for your questions and for your insightful, presentation as well.